This is my wallet, and if I misplace it somewhere, then I can use my smartphone and this kind of like compass to easily find it, because it not only tells me the distance to it, but also in what direction I have to go. This is pretty awesome, and only possible because I got this smart tag in my wallet. And if we look inside that, then we can find two ICs that make this all feasible. One is focused around Bluetooth Low Energy, and I actually addressed that in a previous video. And the other one is the SR040IC from NXP that can do UWB, which stands for Ultra Wideband. This technology makes it possible to figure out the distance between objects, as well as their position to one another. So of course I wanted to try this out by myself, but using the SmartTag IC was not really an option. Instead I searched all over the internet and ultimately pretty much only found two ready-to-use boards or modules that supposedly can do UWB. So in this video, let's test this technology, find out what is possible and what my dream UWB setup would look like. Let's get started! Did you ever felt like ordering professional 6-layer PCBs is too expensive? Well, fear no more, because my sponsor JLCPCB is here, who offers advanced 6-layer PCBs for a great price. I mean, you can get 5 pieces of 100 by 100mm 6-layer PCBs for just $35, which is crazy cheap. But their quality is of course excellent, since each board gets 4-wire resistance tested after production, and you even get handy features like VIA-in pads thrown in for free. This makes such PCBs ideal for high-speed digital, sensitive analog, or pretty much any project you want to tackle. And new customers can also get a $30 coupon on their first 6-layer PCB order. So click the link below and try it out today. Now let's get started with this blue board here, because its price was not only cheaper, but it was overall also easier to use. It is built around the EWM550 module, which has all the ICs and components necessary for this job under its hood, along with of course a suitable antenna. Such an antenna is always mandatory, because we're working with high-frequency radio waves here, in the range between 3.1 to 10.6 GHz max. My blue board, for example, uses between 7.7 to 8.2 GHz, and thus it occupies a band of 500 MHz, which is the reason this technology is called ultra wideband. But anyway, according to the manual of my blue board, it seems to utilize two-way ranging to get the distance information we're interested in. Like the name implies, we need two modules for that. And how this works is that one starts with sending out a message. The second one receives that and answers to that. The first one ultimately gets the answer back, and since it knows the time it sent out its first message and the time it received an answer back, it can use that time difference to calculate the distance. For that though, we also need to know the speed of the radio waves, which is the speed of light, meaning we are dealing with super tiny time differences here, which might be a small problem later on. For now though, I need to configure my boards and tell them their roles. To do that, I simply connected them to my computer using USB-C cables. There, all I had to do was opening a serial communication software and start typing. Now for controlling, the boards come with given AT commands, which is as easy as it can get. So I entered the AT command mode by typing in +++, and then set the roles of the two boards, along with an address, channel, power settings and more. You can check out all my commands here. After that was done, one board started spitting out distance values, which jittered around quite a bit, but they still seemed reasonable, and were definitely in line with the promised accuracy. And I was even quite happy with the indoor tests, because not only seemed the given distances quite good, but it also worked pretty reliable through one 18 cm thick gas concrete wall, but not through normal concrete. And this positive trend actually continued while doing outdoor testing, because even though you definitely need a clear line of sight for this thing to work well, it can go up to 130 meters, which is definitely not bad. So all in all, I would say these boards are easy to use, can do long distances, but are not super precise. But wait, what about the position information I mentioned at the beginning? Well, maybe this black board can do that, which is built around the BU01 module, and that on the other hand is based on the DW1000 IC from Qorvo. That datasheet seems way more professional than the board from before, which did not really have one. But that also makes it more complicated to use, which I realized after finding out that it is using SPI for communication, and that the flowchart for controlling this IC is quite big. But you know what? Maybe the creator of this a bit more expensive board made some great examples and documentation, which of course was not the case. All I found was a schematic, and they don't even tell you how to program the attached STM32 microcontroller. So instead I searched the internet and found this rather old but popular DW1000 Arduino library. To test it, I wired up an ESP32 to the UWB board, according to this wiring scheme, using my patent-pending flying wires that will never come off technique. Once I was done with that, I plugged it all in a computer and uploaded a basic sketch that should output the IC's identifier number. But as you can see, we got no information from it, at which point I suspected that the onboard STM32 was messing with our communication. So I did what every sane person would do, simply remove this thing from the PCB, and just like that, our communication was successful. Meaning you should probably only invest in this bare module if you ever want to try this out for yourself. But anyway, after repeating this process for the second board, I created a sketch for each module and its role, which was not hard to do, since the library does all the heavy lifting. After uploading both, we are once again receiving distance values, which this time do not jitter that much. Awesome! But on the other hand, I quickly realized that there was a noticeable offset between the real distance and measured distance. The reason for that is the PCB and antenna delay, because the timestamp created by the IC when a signal gets in or out is not the same as when the radio wave enters free space. Between that, we got the antenna, PCB traces and a bit more, which all adds up to a small delay in the nanosecond region, which does not sound like much, but when you're calculating with the speed of light, then even 1 nanosecond equals around 30 cm of error. To fix that, I put a distance of 1 meter between both antennas and uploaded a calibration sketch to both, which gave me this number here that I can now put into my final code. And just like that, we got some pretty accurate and spot on values, meaning it was time to do my indoor tests. In comparison to before, I gotta say that these values definitely seemed more precise, but while going through one gas concrete wall was definitely still possible, the range felt a bit more limited. This was confirmed by the outdoor tests, which worked beautifully with line of sight, but like suspected, the max range was this time limited to around 45 meters. But then again, I doubt that I achieved the max range utilizing this pre-made library. But so far I can say that while this module is more complicated to use and might come with a smaller range, it is certainly more precise and offers more functionality. I mean, it even comes with a time difference of arrival technique, which lets you utilize multiple modules to not only find out the distance to another module, but also its position. And no, this is not the technique my smartphone and SmartTag uses, because that uses the angle of arrival technique. That means my phone comes with more than one antenna, and depending on the time difference while receiving the signal, it can basically tell from what angle it arrived. Pretty awesome stuff that not always works super reliable though, which really makes me wish that there would be some commercial bots out there that can do this as well. And that is why I'm currently on the hunt for a suitable UWB IC that I can turn into a maker-friendly PCB everyone can use. So stay tuned for that. For now though, we can conclude that UWB is great, and that the two shown boards can certainly be used for a variety of different useful projects. With that being said, I hope you enjoyed this video and learned something new. If so, don't forget to like, share, subscribe and hit the notification bell. Stay creative, and I will see you next time!